In this video, we're going to be doing some series work. So we're just getting started on our study of series, and really all we have right now is the nth term test for divergence, the divergence test, and some ideas about convergence and divergence and what they mean, and some formulas about geometric series. This first problem is asking us to use the divergence test to show that three of these series diverge. Okay, and so that's what you'll need to do. I'm going to go through and I can identify those real quick and do that, but I'm also going to go and explain why the other ones, the other five, don't definitely diverge because of their terms not going to zero. All right, so the nth term test, to remind you, we're going to say if the limit of the terms, and the terms are the things that go in the series, a, n, if this is not zero, then the total has to diverge. Okay, so then the sum of a n, as n runs from, say 1 to infinity or something, must diverge. I'm just going to kind of keep that visible, because that's the basis of what we're doing here. So I'm looking for terms that don't approach zero as n approaches infinity. Like a, as n approaches infinity, the denominator grows, the numerator stays constant. Okay, those terms are going to zero. Okay, I can't say that that one diverges, even though I'm going to be able to tell you it diverges sometime soon in the future, because of the nth term test. Okay, b, what happens as n approaches infinity? Cosine of 1 over n. This is going to be one of them. Okay, this one. C, these terms are going to go to zero, because if I was going to rewrite this, this would be the sum as n goes from 1 to infinity of n over e to the n. Okay, and as n approaches infinity, the exponential grows faster, and those terms would approach zero. Same with D, the denominator is growing faster than the numerator. E, same story, the numerator's not growing. Sine stays between -1 and 1 forever, right? Whereas log gets bigger and bigger. Okay, so that one, the denominator is growing while the numerator stays constant. Those terms approach zero. F, same degree on top and bottom. This one is, also certainly diverging because the terms are not approaching zero. 5 over 2 to the n, numerator stays constant, denominator grows. Okay, so it's got to be this one, yeah, because the terms are actually getting bigger, 2 to the n over n to the 3. All right, so for B, I'm going to say that the limit as n approaches infinity of 1 over cosine of 1 over n. I can take that limit because as n approaches infinity, okay, this fraction that I'm pointing out right there in blue, that's going to approach 0, so I'm approaching 1 over the cosine of 0, which is going to be 1 over 1. That's not 0, so B diverges. Okay, for F, I'm going to say the limit of these terms is going to be 1/2, because let's say the limit is n approaches infinity of n squared minus 1 divided by 2n squared plus 1. That's a half, and that's not equal to 0. Therefore, F diverges as well. And then the last one, okay, because 2 to the n grows faster than n to the 3 as n approaches infinity, okay, that limit is going to approach infinity. I could say that limit equals infinity, or I could say this limit does not exist, and that's not equal to 0, so H diverges. And it's okay for us to say that a limit equals infinity, but it's not going to be all right for us to equate like say an x or a number to infinity. That wouldn't make sense. But you know that. You've been in this class long enough. All right, so consider the infinite series, the sum from n equals 1 to infinity of 48 times 1/2 to the n minus 1 power. Okay, we're going to write the series as a sum, and that just means like write out the terms, starting with n equals 1. So I'm going to start in 1, 2, I'm going to write 4 terms. The general term And then because it's an infinite series, I'll put a dot, dot, dot beyond. Okay, so at n equals 1, I'm going to have 48 times 1/2 to the 0. And 1/2 to the 0 is 1, so this is going to be 48. Plus, when n equals 2, 48 times 1/2 to the 1, that's 24. And each time, I'm going to multiply by a half one, more time than I had before. So basically, the next term is going to be half the previous term. So 48 plus 24 plus 12 plus 6 plus dot, dot, dot plus, okay, now you don't really have to do this because you've already got this information presented to you in, summation notation. But if we were going to write it as a sum, we could write it like that. All right, and then find S5, the fifth partial sum of S. Okay, so that's when I would be adding up to 5 terms. And so I would say that S5 equals the sum as n runs from 1 to 5 of 48 times 1/2 to the n minus 1, right? What's important there is that. That's the fifth partial sum. So let's say that equals, it's going to be equal to 48 plus 24 plus 12 and 6 and then also 3. So let's see, I'd like to add 48 to 12 to get 60, 24 to 6 to get 30 more is 93. And then thinking about S as the infinite series, what does S converge to, or why does it diverge? Well, S is geometric. Clearly state that. And what's relevant about a geometric series is its common ratio. So we're going to say geometric with ratio equal to, and it's the number that's getting taken to the successive powers. So this is going to be a half, where you could look at the terms 48, 24, 12, and 6, and the common ratio there is 1/2. Okay, now we need to say that, basically, we need somewhere that the absolute value of r is less than 1. That's going to be really important for the justification of our answer. I'm going to say, kind of the next thing is S converges, because I'm not in a hurry or trying to write as few letters as possible or anything. I'm going to say S converges because the absolute value of r is less than 1. Okay? And the value of S is the first term times 1 over 1 minus that common ratio. Still in the shot. So that first term, I go back up here, I wrote out the terms already, that's going to be 48 times 1 over 1 minus a half. Well, that 1 minus a half is a half, 1 over a half is 2, so I'm multiplying by 2 and getting 96. Okay, number 3. This is going to be another geometric series problem. And I know that because I'm seeing that successive terms have a constant ratio. That's what we're saying here. The ratio of an plus 1 to an is always 3/4. And so what you can do is you could say, okay, well, a1 is 24, plus a2 is going to be 3/4 of 24. Okay, 6, 12, 18. 3/4 of 18 is not going to be a whole number, so I'm going to just say plus dot dot dot. This is a geometric series. The absolute value of r is less than 1. That gives me the convergence. We do need to verify that if we're going to use the geometric series total formula. Okay, that's it every time. That's part of the justification. So I'm going to say that this sum is going to equal first term times 1 over 1 minus the common ratio. Okay, 1 minus 3/4 is 1/4. So that's going to be 24 times 4. And that's also 96. Okay, that's interesting. Same numbers? No, 48 times 2. Okay, pretty much the same. Okay, now this next one is a situation that is, I feel like if I pitch it like this could be an AP calculus topic. I could also have written this, series with kind of one term in the sum and rather than like two things subtracted from each other, and we could have split it up using partial fractions, which we learned in this class. I think that would be out of bounds. But this is a telescoping series, is what I'm going to say. So this is kind of like borderline. But we're going to write out the series as a sum, go at least up to n equals 4. But I think if this was to appear in AP Calculus, it would look something like this, where they would give you some sort of scaffolding. They'd have you like write out some terms. 1 over, starts at n equals 1, so that's 1/2 minus 1/3. And if I'm going out to n equals 4, that's going to be 8 total fractions, so I think I need to write it a little smaller and start further to the left. All right, so 1/2 minus 1/3 plus, when n equals 2, 1/3 minus 1/4. Okay. N equals 3, 1/4 minus 1/5. N equals 4, 1/5 minus 1/6. That's as far as I think we need to go. And all right, we're going to show that the series converges to 1/2 by canceling terms. Okay, now that's a little more hint than I think you'd be given on an assessment. But what I'm going to do is first, kind of with the eraser, I'm going to go in and I'm going to kind of get rid of the interior parentheses, so that maybe if you didn't already, you'll see the pattern. And then we're going to kind of think about them two at a time. 1/2 minus 1/3 plus 1/3, well, that's 0. Minus 1/4 plus 1/4, that's, okay, my running total is 1/2. And the more terms I add, I'm always kind of staying at 1/2. Yes. Now, and you might be thinking like, wait, doesn't the partial sum bounce back and forth from 2 minus something to just 2? And it does, but the amount that it's bouncing back and forth is getting smaller and smaller. And I can show you this because we got that calculator situation coming on down here, and that's a reason for us to use Desmos. Just about the only reason I can think for us to use Desmos in a series situation is to think about partial sums. But who knows? Maybe we'll get to a place when we do Taylor series that we'll be interested in that. All right, so to show the series converges to 1/2 by canceling terms, so it's like 1/2. I don't know what you write in there. Maybe I'm just going to cross through that. And, the negative 1/6, we know there's going to be a plus 1/6 coming right after that. Okay, so right, now we're going to go in and, okay, now I need to bring in the calculator. All right, so I'm in a Desmos window, and you can get this summation command by either typing in sum or going into showing the keypad and going into the functions. I think it's going to be down in calculus. Yeah, there it is right there. All right, and it can't do an infinite sum for you because this thing's not here to do the learning for you. But it can do a partial sum, and that's what we're going to do. Oh wait, so I need to type in my actual formula. So n equals 1 up to, I'm just going to say k, and in my terms, 1 over n plus 1 minus 1 over n plus 2. And I don't think we really need to add a slider for k. I'm going to do a table because that's what we're actually interested in doing here. Is S10, S100, S1000, and S10,000. But you could also just kind of manipulate the number here. But what I would like to do is do the table so that you can see. Okay, I need to give this a name. A or f of k maybe. So k and, well, no, x1 and f of x1. There might be an easier way to do this. That's just the way I saw to do it. And, these things with the calculator, you do however you see fit. So I'm interested in k equals 10. Okay, I get 0.417. Yeah, let's put a few more decimals on there. Yeah, 6 decimals. That'll be good. 10, 100.490196. Okay, and equals, or k equals 1,000. I've got 0.499002. And when k is 10,000, I'm going to get 4.999. Okay, one more 9 is staying the same. Okay, that's interesting. Just see what happens. I keep adding more zeros, yes, more 9s, yes, there we go, just more and more and running out. But okay, the more terms I add, okay, eventually I got to the point where it has been fooled and it thinks that I have added up to a total of 0.5. There you go, it's a massive number there. I'm kind of surprised it can tolerate that. But that's what I'm showing, is that the more terms I add, the closer my total gets to 0.5. That's the idea of convergence. Now, if Bn is a geometric sequence with positive terms and B1 is 50 and B3 is 32, what's the total adding from 1 to infinity on Bn? Okay, so that total is going to be 50 plus some second term plus 32 plus dot dot dot. Okay, so what happens each time is we multiply by r. So I'm going to say this is 50r. And if I was going to keep the pattern going, I would put right there 50r squared. And since I know that's 32, that's an equation I can solve. So 32, or maybe I'll say 50r squared equals 32. Okay, so I'm going to divide by the 50. And this is definitely a situation where if you simplify, then your life is a lot better. Okay, these are both even numbers, so 16 over 25, and then you realize, okay, if r squared is 16 over 25, r is either going to be 4 over 5 or negative 4 over 5. But it's Bn is geometric and it's got positive terms, so I know that r is not negative 4/5, because that would cause the terms to be sometimes positive and sometimes negative every other one. So I'm going to use the geometric series total formula after I've justified its convergence. So I'm going to say r equals 4/5. The absolute value of r is less than 1. That gives me the convergence. Okay. And then I'm going to say the total is going to equal the first term times 1 over 1 minus the common ratio, which was 4/5. All right. Then I'm going to say 1 minus 4/5 is a fifth. 50 times 5, that's 250. Okay. Now here is one of the rare situations where we've got a formula for the nth partial sum explicitly in terms of n. Okay, determine if S converges or diverges. Okay, well, that's going to be determined entirely by whether or not the formula for Sn has a limit. So I'm going to say here the limit as n approaches infinity of Sn is going to be n squared minus 3 over 4n squared plus 1. That's 1/4. Okay, so the limit existing means the series converges, and the value of S is going to be 1/4. Notice that like this is Sn, the nth partial sum, the total, not the terms, right? If this was An equals n squared minus 3 over 4 n squared plus 1, we would say the total diverged because the terms themselves were going to 1/4. But this is not what we're saying here. When we say Sn has this formula, we're saying this is the formula for the total after we've added in terms, and we're interested in what number does the total approach as we add more and more and more terms. So that's why we're taking the limit of it. All right. Number 7, we've got a power series. Write p of x as a polynomial. So it's like write out the terms, kind of like we did on the other ones. So starting with n equals 0, x minus 3 to the 0 is going to be 1 over 2 to the first power. So 1/2 plus, when n equals 1, I'll have x minus 3 to the first divided by 2 times 2 is going to be 4. And so that 2 to the n plus 1, that feels exponential. It is. And so each time we're multiplying by 2 in the denominator. Each time in the numerator, we're going to be multiplying by x minus 3. So plus x minus 3 squared over 8 plus dot, dot, dot. I think that's enough. Okay, so you can see it's going to be an infinite degree polynomial. And what values of x make p of x a convergent geometric series? Right, we could plug in different values of x, and if x is, say, 0, we're just going to have, or no, not 0, 3. I was thinking, what if x is 3? If x is 3, we'd have half plus a whole bunch of zeros, right? Higher and higher powers of x minus 3. We know any power of 0 would be 0, so p of 0 is going to equal 1/2. That would have been a really good question for me to have in there. That was a mistake. Okay. You might be working this homework in the future and seeing that the next question is, what is the value of p of 0? And that's going to be a half, or p of 3 is going to be a half because you plug in 3 and you get 1/2 plus a bunch of zeros. All right, what values of x would make it convergent? Think about what are we multiplying by in the numerator and what are we multiplying by in the denominator. That's your common ratio. So ratio equals x minus 3 over 2. Okay, now we can say that the absolute value would need to be less than 1, and we are going to need to solve inequalities like that in this unit and the next. So yeah, okay, so I'm going to say the absolute value of r needs to be less than 1, so x minus 3 over 2 is less than 1. And then we need to think about this and think what's going to cause the absolute value of a number to be less than 1. It's between -1 and 1. So I'm going to say x minus 3 over 2, and I'm kind of going outside of the bounds for this problem, but it'll be all right, is between -1 and 1. I'm going to double all three sides. That won't change anything because I'm multiplying by a positive number. I'm going to add 3. It's less than 4. No, 2 plus 3 is not 4. That's going to be 5. And those will be the values of x that make p a convergent geometric series. Okay, we're going to write p as a polynomial and as a series. All right, so p prime, I'm going to take the derivative term by term, right? And then I will also write out a general term, but maybe we can just do that in the series. Okay, so as a polynomial, p prime of x is going to equal the derivative of 1/2 is 0. The derivative of x minus 3 over 4 is going to be 1/4. And you could either think about it, you know, it's like the chain rule or something, or you could just envision what would happen if you divided that thing by 4. You get 1/4 x minus 3/4. The derivative of -3/4 is going to be 0. Okay, whenever you need to convince yourself of that. Then the derivative of this next thing will be 2 times x minus 3 to the first power divided by 8, right? The denominator wouldn't change because it's like 1/8 of x minus 3 squared. We can take the derivative of that. Think about the chain rule, the inside's 1, so nothing to multiply by there. The next term, okay, the next one would have been x minus 3 to the third, so that would be 3 times x minus 3 squared over 16 plus dot, dot, dot. Okay, and if I wanted to write it as a series, I would say p prime of x is going to equal the sum. As n runs from, we'll figure out the indexing at the end. Okay. Now this might be, you might want to try to write a formula in terms of n, and that's great if you want to, but if you wanted to, you could just take the derivative of this expression here with respect to x. Now it'd be really important that we think about taking the derivative with respect to x, not n, because like that 2 to the n plus 1, that's a constant, right? I could see, people wanting to take the derivative of that, saying 2 to the n plus 1 times log 2 or something. Okay, but what we're going to do, we're going to take the derivative right here, n times x minus 3 to the n minus 1 divided by 2 to the n plus 1. Okay? So, kind of looks scary after you're done, but if you think about it, that's all we did was just the power rule, right? It's the power rule that we've been doing since almost the very beginning. But we might be wise to think about what is n starting at. Okay, n is starting at 1. And that would be, I can see that because of kind of like this right here. I need to start off with the 0 power of x minus 3 to get that 1/4 right there. And so, yeah, there you go. Okay, now the next one I've got for you, I'm going to be integrating p of t. So I'm going to be thinking about just anti-differentiating. Okay, now if you wanted to do it, plug in t, take the integral, plug in x, plug in 3, and subtract, that'll work for you. To find the value of c, it's going to be 0 though. I'm just going to tell you, if we integrate from this, basically the centering point of the power series, and we don't know that much about power series yet, I'm going to let that be the case, but the point that would cause you to plug in a bunch of zeros, if we start our integration there, it's just an antiderivative with c equaling 0. So n of x is going to be 1/2 x, because the antiderivative of 1/2 is going to be 1/2 x, antiderivative of constant, plus add 1 to the power, divide by the new power. X minus 3 squared divided by 2 times 4. And I'm actually just going to leave it like that because it'll make it easier for us to write as a series if we need to write a general term or whatever, which we will. X minus 3 to the third dividing by 3, and there was still an 8 down there, and I think that would be enough for us to see the pattern. I can also say that the antiderivative of p with respect to x is going to be, I could look at this general term and say, all right, x minus 3, add 1 to the power, n plus 1, divide by the new power, throw an n plus 1 in the denominator. All right. So the sum as n runs from, I'll reserve judgment, but I think, yeah, it might be best for me to just say, okay, x minus 3 to the n plus 1, okay, add 1 to the power, divide by the new power, and that thing is just still divided by 2, and divided by 4, and divided by 8 in the denominator. All right, and so what are we starting off with? The first power of x, that would mean that n would need to start at 0. Okay, now that was a, relatively challenging one, especially for where we are at this point in our study of series. So, like that's probably as much as we're going to be interested in this homework as far as challenge. All right, so it is known that the sum from 1 to infinity of 6 over n squared equals pi squared. What is the value of the sum from 4 to infinity of 1 over n squared? Oh, this is great. So this first series, which maybe I'll call that A. A is telling me is that 6 over 1 plus 6 over 4 plus 6 over 9 and 6 over 16 and so on forever, that adds up to pi squared. It's interesting. Okay, we are pretty far away from being able to understand why that's true with the math knowledge we have right here in this class, but stay at it and you will have the tools. You're really not that far off. You've come over halfway, I would say. But there's some interesting videos about it on the internet too. That's the type of equation that we're not going to be finding those results or proving them or really working with them at all. This is kind of a one-off problem. All right, so that's equal to pi squared. This sum that we are interested in, I'm going to call it B because this problem is right at our level. Okay, b is 1 over 1 plus 1 over 4 plus 1 over 9 and 1 over 16 and so on. So I think what you're supposed to notice on this is that b is equal to 1/6 of a. And, oh, but b is not, b starts at n equals 4, which is, yeah, that's kind of the whole point of the problem. Okay, so that's going to approach pi squared over 6. Yeah, and b starts at n equals 4, which is going to be 1 over 16 plus 1 over 25 plus, let's see, 6 would be 1 over 36 and so on. Okay, so that's, I'm trying to solve that equation, or put in the, missing piece of that equation. I think what I should do is probably get rid of these dot dot dots and give myself a little bit more room over here and write out some more terms. Yeah, I think that'll be good. So I've got 9th, 16th, 25th, 36th, plus dot dot dot. Okay, really what I'm interested in is starting here and, holding on to including that dot dot dot. So I need to just get rid of the 1 over 1, the 1 over 4, and the 1 over 9. So I'm going to subtract all three of those from both sides of the equation and say that's pi squared over 6 minus 1 minus a quarter minus 1/9. Okay, now I think that'll be far enough for our class, but if we needed to put this together with a common denominator, that would be 6 pi squared. Okay, my common denominator is going to be 36. I'm going to subtract, okay, that would be 36 36ths, 9 over 36, and 4 over 36. Okay, so that would be a total of 49 over 36. Okay, great. It's not that much more simple than the expression I had before. All right. Number 9. A ball is dropped from a height of 25 feet. Each time it falls h feet, it rebounds 2/5 h feet. This is going to be a geometric series. All right, so yeah, total distance traveled by the ball, because it's just like, that's a flat wall. This is the floor. That's going to be the ball. It's just going to drop down and then bounce back up and then go straight back down. So the total distance traveled is going to be like the total vertical distance traveled. And okay, so each time it falls, it rebounds 2/5 h feet. So I've got 25 is the first fall, plus then it's going to rebound to 2/5 of 25. And that's going to be 10 feet. Okay. But it goes up 10 feet, it's got to come down 10 feet, plus, and then 2/5 of 10 is going to be 4, and another 4 when it comes down, and then it's just going to keep going like that. Okay, so this one has got a little bit more going on to it. I kind of remember this problem from a previous year. So 25 plus, really it's kind of 2 times a series. Now, you wouldn't really need to be able to write this as a summation, right? But if you did want to, you can say, okay, I see it's starting at 10 and it's got a ratio of 2/5. Okay, if you do that, then you need to have the exponent be n minus 1 if you start at n equals 1. You could start at n equals 0 and have the exponent be n. It really doesn't matter. Because what we're going to do is we're going to go over here and say, okay, 25 plus 2 times first term, 10, multiplied by 1 over 1 minus that common ratio, plus 2 times, this is going to be 10 3/5, so 5/3. All right. So 50, 100 over 3, so 25 plus 100 over 3, so maybe 175 over 3. All right, number 10. So multiple choice question. And because it's got these exponential aspects, it is going to be geometric. Okay, that's the big connection, is that a geometric series, it looks exponential with the variable being n. All right, so, there's ways we could rewrite this, as a fraction to see what the common ratio is, but I actually think the best way is going to be to write out terms starting at n equals 1. All right, so n equals 1, e to the negative 1 plus 1 is e to the 0. It's 1 times 2 plus, when n equals 2, I've got negative 2 plus 1 is e to the negative 1 times 2 to the second is 4 plus e to the, when n is 3, negative 2 times 8, and so on. Right. And thinking about what I'm multiplying by each time to get from one term to the next, it looks like I'm multiplying by an e to the negative 1 and by a 2. So that's 2e to the negative 1 is 2 over e, and e is a number that's bigger than 2. So that means that the absolute value of r is less than 1. So I have a convergent series. So I'll get rid of that answer choice. And say the total is going to be the first term, 2, multiplied by 1 over 1 minus the common ratio. Okay, and that's just going to be 2 over 1 minus 2e. And I think what we would be wise to do here is multiply by e over e. Yeah. We can't be like going around and changing this fraction, but we could multiply it by, an appropriate form of 1 and see that I'm going to have a 2e in the numerator, and when I distribute the e over the 1 minus 2 to the e, I get an e minus 2. And that's going to be one of my answer choices, 2e over e minus 2. There we go. Right, now, number 11. The function f can be written as f of x equals a over bx plus c, where the values of a, b, and c. So this is, we can rewrite it because it's a geometric series. Okay, so provided that, x minus 3 over 1 is between negative 1 and 1, the first term is going to be 4 times that to 0, because 4 times 1 over 1 minus the common ratio. X minus 1 over 3. Okay, and that's going to equal 4 over 1 minus x minus 1 over 3. And I'm going to take that same strategy I just took and multiply by 3 over 3 to get it in like some sort of usable form. And that's going to be 12 over, distribute the 3 over both terms. I'd have a 3 minus, I need to use parentheses, x minus 3. Okay, so 6 minus x. 12 divided by 6 minus x. And that means that a is 12. Is negative 1, and c is equal to 6. Okay. Right, now we just got some more geometric series work. That's good. We definitely need some of this. So first we're going to examine the common ratio. We see it's exponential, and this, maybe you're thinking, okay, the exponents are different. Maybe it's not a geometric series. And if you were concerned about that, you would just write out a few terms. Pi to the 2 over 4 to the 0 plus n equals 2 pi to the 3 over, n equals 2, 4 to the first, n equals 3 pi to the 4, n equals 3, 4 to the 2. Okay, and I think that's enough to see that there is a common ratio. The common ratio is pi in the numerator and 4 in the denominator. And again, the absolute value of r is less than 1 because 4 is bigger than pi. Okay, so that gives me convergence. And then, let's see, the value of a is the first term multiplied by 1 over 1 minus the common ratio. And you could stop here on the quiz, but again, this is almost certainly going to be a multiple choice type question, so I would recommend being able to simplify this. So I'm going to have 4 pi squared in the numerator and 4 minus pi in the denominator. Now, does this series converge or diverge? Well, we're not. If not asked to find the total, we're not going to find the total. If we decide that it converges, okay, we're just analyzing the common ratio, but we see that 2 to the 2n. And it's like, okay, how's that going to impact? We saw that like adding 1 and subtracting 1 and subtracting 2 didn't really change the ratio. Oh, whoops, we didn't even do the one on the right. Okay, but it's not going to change the ratio. That's what we're going to find over here when we do this one. I'm going to write out some terms. Yeah, 3 to the 0 is 1 over e to the 2 plus 3 to the first over e to the third, and n equals 4. That's 3 to the second over e to the 4, and so on. Okay, notice that the common ratio is 3 in the numerator and e in the denominator. And e is a number that's between 2 and 3, so this ratio is bigger than 1. Meaning the series diverges. All right, there we go. Okay, but notice that on these, the ratio is still pi over 4 and 3 over e. Okay, but when we go over here to this 2 to the 2n over pi to the n, okay, we're going to see that that common ratio is going to be different. Okay, so let's start by writing out terms. It's always a good idea. Okay, anything with 0 is going to be 1, so my first term's 1. Then when n equals 1, I've got 2 squared divided by pi to the first. N equals 2, I've got 2 to the 4 divided by pi to the 2, n equals 3, 2 to the 6, divided by pi to the 3, and so on. Okay, so we see that the ratio here is in the numerator 4, and the denominator pi. Okay, pi is between 3 and 4. The absolute value of r is greater than 1. That's going to give me divergence. F of x equals the sum from 0 to infinity of x to the 3n. Find the value of x to the negative 2/3, or explain why it diverges. Right. Well, I'm just going to write out some terms first. F of 2/3 equals the sum from n equals 0 to infinity of x to the 3n, where x has been replaced, pardon me, x has been replaced with negative 2/3. Okay, and that is going to be, okay, that's the same based on what we saw in the last example of the actual ratio is going to be negative 2/3 to the third. Now we can do that, and it's going to be, take negative 2 to the third and take 3 to the third, so that's negative 8 over 27. Okay, the common ratio is negative 8 over 27. The absolute value of the ratio is less than 1. That will give me convergence. And I can use the formula for the total, and this is going to be equal to the first term. That would be 1 multiplied by 1 over 1 minus negative 8 over 27. All right, so 1 is 27 over 27. I add 8 more, and I'm going to get 35 over 27. So 1 over that would be 27 over 35. And that looks like it would simplify, but it definitely does not. All right. If A and B are positive numbers, what conditions on A and B would guarantee that the series converges? Okay, so if it was a geometric series, that's pretty much all we know right now. And we can see that these are going to be geometric series because n is the exponent. We just need b over a to be less than 1 in absolute value. But I think, I remember there's a disclaimer that they're positive numbers, so we just need a to be bigger than b. I think it's actually easier to just think about it. You know, if a is bigger than b, then b over a is going to be, less than 1. Assuming a and b are both positive, which we are. All right, now a squared over b, we would just need b to be we need the denominator to be larger. So b is greater than a squared. Okay, that would be a condition that would guarantee series convergence. Okay, and look at that. That is all. Okay, so I thought there was another page. This is great. Okay, so that's going to be all for this video. Thanks for watching.